Okay, we have the very basic theory I wanted to discuss for the regression, mainly because it's useful to know because it's the most abused method of statistics, I think. Everybody uses it, but I'll be damned if they know what they're doing with it. What we have, we'll start with the simplest form. It's a simple linear regression. Linear means the relation is of the first degree, even with some transformations can remain the first degree. We have other types that are logistic regression, for instance, which is mediated through logarithm or exponential functions, or some other transformation, the Probit transformation, which is a normal distribution transformation. These are not linear, but most of the regressions are linear. So what we have two variables that are somehow related, the y and the x, or we think we are related, or we want to see if they are related. So we have pairs of the observations. Now, in order to work the regression, there are certain assumptions that are sine qua non. What do I mean by that? The first is the most important. The expected value of the errors has to be 0. Think of it, my feeling is that the easiest way to understand it is to have a measurement process. So let's say we have 100 pieces of wood that we know their exact measure because we did it with lasers or whatever. We took it to Switzerland, to that place where they keep the measures and the weights, and we have the exact measure. And then we take 1 meter from a hardware store and we start measuring the pieces. Okay? For each one of them, a little error measurement will come to be. We didn't handle the tool well. The tool itself must be might have a problem, whatever. So the first thing to understand is that the two measures that we have, the x and y, are related, are referring to the same underlying object. Okay, I cannot regress x and y when the x refers to one thing and the y refers to another. They must be connected. And the error of this relation must be 0. The expected value of it. In other words, I don't have a systematic error. What would be a systematic error? If, as I told you before, my measuring device had a mistake in the calibration. So where it said it's 1 meter, it was actually 1 meter and 2 centimeters. That would be a systematic error that will reflect in other measurements. And so that's no good, cannot do a regression. The second, and I'll use my computer in a minute back to show you what it means, is that the variance must be the same for all values of x. Because, remember, we did something in Excel. Oh, I can take this, doesn't matter. Is the death rate and the vaccination rate. This is the regression line, okay? What I want to have is that the variability in all parts of the line has to be the same. I don't want to have one variability here and another variability there. Okay, that creates a problem in my ability to derive the distributions of the estimators. It might not invalidate the line itself, because the line is constructed in a mathematical way using least squares, for instance. We call it ordinary least squares here. So the line itself might be valid, but the properties of the estimators might not. So I cannot draw conclusions from the estimates I wanted. I cannot do hypothesis tests. I cannot do confidence intervals, etc. So that's why I need to have that common variance. Okay. And I want the values of the errors to be uncorrelated. Correlated means, in other words, they're not related. It's not that if I do a mistake in the beginning, that goes and propagates itself to the next measurements, and so it becomes bigger, okay, or smaller, whatever. The last part is very important. I said to you that the variable x is not stochastic. I don't know how many of you have heard some mixed effects models that they do sometimes in statistics, where some of the variables, the independent variables, are just not stochastic as this. Some of them are stochastic. Why is that important? Because it affects the variance. In this model, if I take the variance of y, this part here is constant. There's variance 0. And so the variance of y is the variance of the errors, which I write to you down here. Okay? If the x is stochastic, it contributes to the variance. And that creates a problem in all the calculations we do, makes them much more difficult. Okay? Because we have two components on the variance, and this raises some issues if that thing is a constant variance also, or if it differs for parts of x, etc. So it's something that makes the solution of the problem much more difficult. Here, I write you the answers. I did that because I was thinking of doing some prediction, but then I decided not to do so. These formulas are just to see that they are already complicated. And imagine how much more complicated it would be if we try to have a second and a third independent variable. Okay? So we don't solve them like that. We solve them using matrices, and generally we'll solve it with programs, not by hand. I think of all these poor souls in the 19th century that were doing regression, and we're doing all these things by hand, you know? So let's see how we do the regression, the simple regression. I can erase this here. So one critical issue. Regression is the only structure-sensitive procedure in SPS, in Excel. The variable has to be in columns. If it's not in columns, we're going to do a mess, and I'll show you in a minute how we can make that mess, because I like to make messes sometimes. Let me get this. I'm not gonna get them all. Say I have put them like this, okay? And then I told it to do regression. First of all, I'll try to do it like that, and hopefully it will start complaining, but if it doesn't complain, I'll see how it will do it. So here is the death rate is my independent variable, and this is my open range. Όχι εδώ. Θα βάλω από εδώ κάτω. Shoot. What does it say? Input X range cannot contain more than 16 variables. That's no problem. I'll cut some. Let's go again. It did it. Miracle. But what has done? A total mess. Why? Because it said, okay, sir, you gave us the way you did it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 variables. It thinks it has so many variables. And then total vaccination thinks it's a variable. And it thinks that these things are variables too. 25, 20, all these, the numbers from down here. All these things it thinks they are variables. Okay, different variables, and that's their name. And tries to do the calculation. Okay, doesn't work like that. What it does, it needs them as columns. So let's do it now correctly. That analysis, we'll go here where it says regression. Okay, now first wants the y variable, this thing here. And then wants the x variable, which is this thing here. Okay, let's say I put a different sheet here. Okay, well, I have everything. Let me show you. Here it has certain plots. In the notes, I don't have them, but I'll put them here just to discuss them a little. Okay, here we are. Here are the results of the regression. When I do it in Excel, the first thing I do is go here where it has these things and I delete them. They are completely useless. They are confidence intervals on the variables, but they don't offer any information and they repeat themselves, by the way. Wait a minute. All right. So what do we have? First, we have what we call goodness of fit statistics. In other words, this multiplier, I wouldn't look at it if I were you. Το μεγαλώσω. Okay. Because the way the Excel calculates it, it takes the root of the R squared. Doesn't calculate it from what it is, because that's the correlation coefficient. Now that I have two variables only, one dependent and one independent, because it should be negative. X and Y are in negative relation, so that's why it's misleading. Here is the R squared. That is the coefficient of determination, and it tells us the percentage of the variance of the dependent variable, the death rate, that is explained by the independent. Okay? Get back at it. And then we have the adjusted R square, which does the following thing. The way the regression is structured, as we enter variables, automatically that R squared becomes bigger. The more we put, the bigger it gets. But that can be misleading, because if you think of it kind of, in a very simplistic way, if you have one dependent and one independent variable, you have 100 observations, all these 100 observations have gone into estimating the coefficient of that one variable. If you put 10 independent variables, now they have to share the estimating process. So roughly speaking, 10 observations go for each estimator. And if you had 100 variables, you had one observation go for each estimator, which means that the more variables you put in, the worse the estimation becomes. So you have to create a balance between how many variables you should put in to explain the variation, but not too many to degrade the estimation quality. That is captured by the adjusted R-squared. So as long as the R-squared goes up or doesn't go too far down, you're in business. You're doing better. If it starts becoming very small, then you should look at fewer variables, okay? Now, the second is the ANOVA. Here that I do a single regression, it's redundant. I could live without it. What it does, it tests simultaneously for all the betas of the regression, these values here. Okay. In multiple regression, I might have 10 of these. The analysis of variance will test that all 10 of these are different than 0 as an alternative. Versus at least one of them is 0 for the null hypothesis. So it does the calculation, got a pretty good significance, as you can see, 3 zeros and 1. And what does it tell us here, if we were to understand what we're reading? It tells us the following. The intercept tells us that if the value of vaccination was 0, okay, we would have 5,700 deaths for a country with 0 vaccination, okay, per million. The coefficient now, that was 13.7 something, negative, says the following, that for every % raise in the vaccination rate, you get 14 less deaths per million. Okay, which I think was quite important. And the other way around, drop, you have a rise in deaths. So what we see here, both ways, if you look at this table, the size of the p-value, okay, and the R-squared, shows you a strong relation between vaccination and death rate. Okay, these are the true data. I haven't done anything with them. Now, here it has put out the residuals, okay, which is the difference between the observed and the estimate of the regression. These are the residuals. And as you can see, if I collect them all, the mean value is 0. If you can add them first. See, this calculation error is actually by definition 0. Okay, and the same thing I think holds true for the standardized. Even standardized means we take the average, we subtract the average, and we divide by the standard deviation. Okay, this is the standardization. Now it created some plots which might be interesting to see. Oops, sorry. If I manage to put it someplace here, let me make it a little bigger. Sometimes you might want to see them. When you look at this residual plot, what it tells you is that it's kind of symmetric around 0. So we don't have a systematic error. There's not something systematic missing. What would be systematic if we would see a pattern like this. Still means 0, but with a shape. That will tell us there's another variable hiding someplace which we didn't use. Okay. Here's the regression line. Now, of course, use big things and we don't see it very well. But I didn't get them become smaller anyway. This is the regression I showed to you before as well. Just shows you how it goes. And this is my favorite. The normal probability plot, it will be nice to put a line here. The question is how close to the line is. The line should actually start from 0, but this is a measure how close to the normality assumption we are. And this is pretty decent. Okay? What it plots is the expected percent and the observed percent under the normal distribution assumption. Okay, so it's kind of okay. Now, I thought I'd try to show you some multiple regression as well by adding one more variable, which is the GDP measured in purchasing power parities. Okay, let me show you something. Say I wanted to do only that. Show you another peculiarity. Okay, input range I'll leave the same. Here I go to that. Okay. Τι έκανε κανονικότητα. They did it just fine, no problem. Not as good as the vaccination. Okay, but it's still good enough. In other words, you can see it has a 35% variance explained, negative coefficient again. The richer have lower cases. Okay, and the F value quite smaller than 0.05. Okay, so the question is, what will happen if we use both? Do the typical multiple regression. Now I have two independent variables, okay? Now let's see what happened. My R squared improved. From 45, it went to 57. And the adjusted is higher, it's 0.53 from 0.42, whatever it was before. What was it here? 0.43. So it went to 0.54. So I have an improvement. So it was worthwhile putting the second variable in there. Okay? The significance became much stronger than before. Okay? And it's 4 zeros 37 compared to 3 zeros and 1. Okay? So it went down one level. But now that I have two variables, they are not equivalent, the two. results, look at what happens here. This is the significance of the ANOVA. The same is the significance of the statistical size of the total vaccination, okay? The same p-value. The ANOVA gives the same result as the test for the coefficient, okay? Here, the ANOVA is this, the test for the coefficient, where are here, 0, 0, 18. Okay, so what this has tested is a test that beta 1 and beta 2 are 0 against at least one of them is not 0. It has done a simultaneous test the same way that ANOVA tests for the means to be all the same against one of them to be different. Okay, so this is the test that both of them are 0 against at least one of them is not 0. Whereas here, the test is the particular is 0 against is not, and here is the other one is 0, it's not. We can see that they are both negative. But the values have changed. That was minus 14. Remember, it became minus 11. This is minus 18. I think it remained roughly the same that I have before. No, it was minus 28, 200 and, what is it? Make it per thousand. Understand what it is, because when I say it like that, I don't. Yeah, minus 28 it was, okay? And here it is minus 18, because the impact was split between the income and the vaccination rate. That's why each one of them contributes less. What's the question, ladies? To the teacher, not to each other. Go ahead. Tell me. The intercept is if these two are 0. So nobody's vaccinated and are dirt poor. Then we'd have 6,135 deaths from COVID. Okay, because here's the model. See, I will write the model. Oops, multiple regression, further down, further down. See, this is the model. If all these things disappear, are 0, then this is the intercept. So it's the number of deaths when all these things are 0. Okay? What is interesting is how we interpret the coefficients. Okay? In other words, the intercept, that was the number, okay, that you asked me. If we had vaccination 0 and income 0, we have. Now, the coefficient of the vaccination is the change that happens in the death rate for each change in the vaccination, given that the other variable stays the same. So you can think of it as a stepwise process where we can have this income and the other income. If we compare the same income and we change the vaccination rate, that the change you see in the coefficient. That's the value of the coefficient. The change in the death rate, if you keep the income the same, you cannot change them both. Okay? And it works the other way around. If we keep the vaccination rate the same and we change the income, how much we'll see the change in death rate? Yes. Well, there are cases where it would be logical to assume that if you have no independent variable, you have no response. For instance, what can I think of? Let's say I want to measure the change in the length of, I'm measuring the ability to extend on a metal that I apply force, okay? And so I want to see how much it will extend it if I apply force X, okay? Now, if I apply zero force, I will expect zero extension. So there, I can enter that as a limitation of my model, that zero will correspond to zero by definition. I won't allow the randomness of the results to move that point that should be 0, 0. Yes.
That's like the academic answer, empirically speaking. Some people do that just to manipulate the model and increase the explanatory power.
That's cheating.
Okay.
That's
But
cheating.
if you have seen that, yeah.
That's cheating. Yes, it makes the R square bigger. You want to see it? Let me show you. Let me show you. We had about 50, right? Where are we? Data analysis, regression. Constant is 0. Okay. No int. Let me see. Yeah, see? It was 53, right? Now it became 64. And the significance became bigger, etc., etc. But we lost the impact of the GDP. The reason is that and the coefficients, it's extremely interesting results. I need to. This became positive, and this became positive. Why did that happen? First of all, the vaccination is statistically significant, but the income is not. Okay. Now, what really happened is that these coefficients, the variables, tried to absorb the effect of the constant term that we killed. Which constant term, by the way, was 6,000. Extremely statistically significant. We should not have made it 0. Okay? We had a line that was like that, and we took our hand and grabbed it by the tail and pulled the tail down to 0. What happened to the line? It was forced to change direction to accommodate for the data. Okay? So that's why we use that in very specific cases where the logic says that the 0, 0 point is the point that the line must go through. In our case, it's clearly that it shouldn't go through that, because if we don't vaccinate, more people will die. So when vaccination is 0, the constant term must be higher. Okay? Yes, Maria.
No. What's the behavior in this case with the omission of the intercept? What's the graph for the 0?
Well, you see that it. How can I put it? Let me go here. When you look at it, it looks okay. It gives you a bigger R square. Okay, it says that the GDP is not statistically significant. Okay, but this is statistically significant positive. There's a positive relation between. The data doesn't show that. When you plot the data, you don't see that. You see the opposite picture. And I'm saying that that happened because you imposed a condition that was patently wrong. Okay. Even if I was doing it, look at this. Now, let me erase this because I'm going to put it in the same place. And I'm going to do it. Where am I? Data analysis, regression. We're going to do it only on the vaccination. Okay? You see what happened? The data goes like that, and you force it to go like this. Now, since we anchored the regression at this point, it did its best to fit the data. That's the best effort to fit the data, given that it had to start from here. So the picture is clearly wrong, and that can tell us how wrong were we to select zero intercept. Maria, you want to say? Huh?
You can also add the trend line on the blue dots too.
I can put a trend line, but the trend line,
It's for,
it has the intercept the 6,000 that we have.
yeah, just to compare them. It's the original one.
Yeah.
Yeah, my question is that if we add a variable and we increase the power of the model, the expanded power of the model, but at the same time, the variable that we added has a p-value greater than 0.5. Yeah,
You shouldn't have it.
so we should drop it.
We should drop it. Since we are in a playful mood, let me show you. If I can find it. What Maria said was the following. What if I put a variable that's not working? So I basically put a random number here. It should not be related at all to the death rate, okay? In E. I have three variables here. Look at what's happened. I'll be damned. This is extremely funny. Shouldn't have happened, but it happened, so I need to change it a little. I put a completely random variable in there. Okay. And it was very statistically significantly related, so much so that almost kicked the others out, but didn't, and put the explanatory power of the model to 90%. Okay, so I don't know how this happened. Not right. How can we fix that? Now I think I fixed it. I think I fixed it. Don't count on it. Yeah, I screwed up the model completely. That was a very good objective. Very big significance. the adjusted square, okay, but p-value is completely out of whack. Now, what I would do if I was doing the analysis, now I know this is a screwed up variable and I know this is what I should take out. But if I was doing it in an analysis that the variables came out from their own free will, I would erase this first, the one with the largest p-value, okay, and then try the others. But as you can see here, wait a minute, no, I'll take it back. Wait a minute, we have an error here. And that's why it happened before. I think I forgot to erase this. Huh?
Do you remove the variable if it makes sense to the theory that you're testing?
No, I'm looking at statistics first before I do that. No, maybe before it was okay to it because I had made it go through zero. That's what was creating the problem. Okay, here, but this is good. Okay, this shows better what we want to see. So I put an extraneous variable that shouldn't be there. Okay. First of all, I can see it's not statistically significant, so that's one criterion to erase. Second, here I had adjusted that square 0.537. In this, I have 0.52. The adjusted square has dropped, whereas the R squared by itself has gone up, I think, 0.5755, 5729. Okay, the R square went up, but the adjusted R square went down, saying that the new didn't add to the explanatory part of the model, but subtracted. Okay, and since its p-value is smaller than 0, then I should get rid of it. Okay, this doesn't belong to the model. Okay, any questions? All right, we can go to the last part of the course, which is the sampling methods. Now, the sampling methods pose some very interesting difficulties in the analysis process. In some cases, the process is very simple. In other cases, it's quite complicated. Okay. As I said to you in the beginning of today's class, what we have is a situation where we need to know the probability structure of the sample, how it came from the population. Okay. And that will inform the types of estimates we use and how we analyze them. We'll see only two methods. There are many more than two. I'll give you an example of what I mean by many more than two. When you try to study illegal immigrant populations, how do you sample them? I'm open to ideas. You don't know how to sample them. Huh? Well, the method is street workers take the questionnaire, give it to Carmen, and tell her, here are 10 more questionnaires, give them to your friends, and I'll meet you at this corner next week to give them back to me. That's a sampling method, the probability structure of which is up for grabs. Okay? In essence, we assume randomness, and that method generates its own probability structure. Because, for instance, you find 20 Carmens, and one of them brings you 10 questions back, the other brings you 5. Says, I couldn't find anybody else, or I didn't have any other friends. And so now you know that in different parts of the country, you have different number of people. Okay, you can get, if it was easy to get them at one part, that means that there's a higher concentration of illegal immigrants in this part of the town. Okay? So, what we'll do, we have to understand what we're talking about, first of all. Population. Is the population of the study, and we want to describe it or measure certain characteristics, etc. Give you an example, which I liked because I fought over it and I lost. A few years back, we did a study called MORE, Mobility of Researchers in Europe. In the team, we were people from all over Europe. We Greeks had the upper hand because we were Greeks from Greece and then Greeks from Austria, Greeks from Ireland, and various Greeks. And at the end of the project, we found out that the Belgian chief of the project had finished Lyceum in Greece because his parents had come here to work. So he was Belgian, but he spoke Greek. We set up the questionnaire, trying to find the mobility defined as having spent more than 3 months in a country different than the one you got your PhD in. And we set up the questionnaire, and then we'll start discussing what language should be, etc. So we said we shouldn't have it many languages because there will be problems in the translation and might be difference in the translated versions, etc. I had the fear, having lived in the States, Northeast United States, for 14 years and having been exposed to Canada, I was sure that the French will not answer an English written questionnaire. And so I said, maybe we should entertain the thought of translating it to French. I said, yes, but if it's French, then we should do it in Croatian and blah, 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 blah. I said, what are you going to do? Take the prevailing language of the team? We should send it in Greek. Anyways, we sent it in English. The response rate was what we expected, except in France, which was 1/10 of the expected rate. So we wanted to boost the sample in France. So what did we do? We went to the database with the FP 5, 6, 7, 8, whatever programs, and we sent it to them, altering the population in the process. Why? Because the random population was all university staff in Europe. In France was the university staff that was involved in the exchange programs of the European Union. So they had a much higher propensity to have moved around, which came out to be the proportion of French people have moved was pretty high. Okay. So another example from Great Britain there, United Kingdom, although you're young, you don't remember it. When John Majors had his first election, the polls had him losing by a big margin, right? And he won. Why? Because the pollster, being cheapskates, went to the households in the morning time, so they will not pay overtime the researchers to do in the afternoon or at night. But in the morning time, who did they find at home? Housewives, students, people not having work. In these groups, labor had over 60%. Who didn't they find? Working people, other active population, where the conservatives have a much better percentage. So the population they sampled for the study was half the voting population and even less. Okay? So we have to have a very clear definition of what the population is when we try to study something. Okay? The second thing we need, ideally, we don't live in an ideal world, is a sampling frame, a list that has all the members of the population where we want to sample and the means to contact them. In the aforementioned study I told you about mobility, what we would like the European Union to give us would be a book that will have every researcher in the union and his telephone or his email address. Of course, they didn't have it. They didn't have even a list of the universities and their departments. And to make things even better, the names of the structures of the university differ by country in the union. So here we have the University of Athens. The university is made up of entities that we call them scholae. The official translation is what? Faculty? It's faculty. The official translation is faculty. In the States, they call it school. In many other countries, they did call it school. Each school is made out of departments. But in other places, the departments are called divisions. And then the departments are made up by sectors, where in countries where they use the word department for department, they may use the word division for the sector. A mess. Anyway, through that mess, we try to develop a sampling process. What we did is we went and we found all the universities ourselves. But we couldn't get to the staff because they don't list the staff, everybody. And so what we did is we tried to get all the departments of the university, and in an automated way, which led to some funny parts. For instance, in some Italian universities, the name of the department was open the next window, because they were doing it automatically in the browser, and the browser told them to open the next window for the department, and that was listed as the department's name in the database. So we fixed that. But anyway, that method we will not discuss that we use there. It's a more complicated. Then we want a sample. I use the word that everybody uses, representative sample. But what I want to say is a probability sample, because representative samples cannot be had. When you think of a representative sample, you want a sample which structure will be the same as that of the population you want to study, right? But if you know the study population structure, then you wouldn't need to do the sampling method. If I want to find out the percentage of people that are in favor of, I don't know, Hamas in the Gaza-Israeli war in Greece, if I knew that percent, I wouldn't want to do a study. If I want to get a representative sample will be the one that the percentage of people in the sample that are in favor of Hamas is the same as the percentage of the population. That will be a representative sample. It will represent the percent, but that cannot be done. What I can do is I can get the probability sample, where I know the probability of each member population to be included in the sample. And then from that, I can create the correct estimate of the proportion of the sample vis-a-vis the population. Now, I need to know what the sampling unit is, person, an object, or something else. A stratification variable, which refers to one method of sampling, and that is, if you think we want to do a study in the European Union, we want to have observation from all countries, then the variable country is a stratification variable. Tells us that I take separate samples from each country. Okay? And then I have cluster. If that word points toward agriculture, it's not by chance. That's where it came from, clusters of trees. That's where the word was first defined. And in essence, came out when they wanted to do in botanology studies of areas. And when you take an area and you cut it up in parcels, if you go randomly, you understand pretty quickly that, say you want to study a fir tree, okay, in Yellowstone Park in the States, and you want 1,000 trees. Can you imagine? You're going to go into a helicopter. You're not going to walk to find 1,000 trees throughout Yellowstone, which is about the size of Greece, if not bigger. And you're going up and down, chasing its separate fir tree to see its health. Okay. Well, the cluster method says you can do something smarter. Go cut up the thing in pieces and create areas, small areas, where you'll expect to find clusters of fir trees. And select all the fir trees in the cluster or a subset of the fir trees in the cluster. And thus you get the sample size you want, but you do 1/10 of the trips that you had to do. That method that developed then is the method of choice for public opinion polls. Why is that? Because the list of the voters doesn't exist with contact details. Yes. You want to have a break? Okay. Okay. I'll stop talking. Now, please. Γιατί είναι
Θυμάμαι σε μια έρευνα που είχαμε κάνει, το κάνανε μετά, όχι δηλαδή ερωτηματολόγια και τα λοιπά, Bassiakos ενημερώνει για την επιλογή στην πρώτη. Άλλο αυτό.
Έλα ρε Αγνή, τίποτα, κάνω ένα μάθημα σε κάτι ξένους από ένα ερευνητικό πρόγραμμα, τώρα έκανα ένα διάλειμμα και είδα το τηλεφώνημά σου. Λοιπόν, θα έρθω αύριο από εκεί να δω τι γίνεται και θα φροντίσω να έρθει και ο υδραυλικός. Αυτός που ήταν να βάλει τις μπάζες δεν έχει έρθει ακόμα? Να το μαλακά. Μου είχε πει θα έρθει μέσα στο Σαββατοκύριακο, μέχρι το Σαββατοκύριακο, τέλος πάντων. Καλά. Εντάξει, θα έρθω αύριο το πρωί να δω τι γίνεται. Εντάξει. Θα κοιτάξω αυτό πρέπει να ψέτρε. Εντάξει, έγινε. Θα πούμε αύριο.
Καφεδάκι.
Από το δικό σου εδώ δεν χρειάζεται. Δεν ξέρω.
Space for the latest section.
Σχεδόν έχω ερώτηση. Αν έχετε δουλειά, θα περιμένω. Σχετικά με το COVID, το έχουμε λησάξει τώρα και για το COVID, για όλα το COVID. Έχουμε λησάξει, δεν έχω πει από πάρα πολλού διαφορετικού ότι και καλά, ξέρετε τον καρκίνο και δεν ξέρω και εγώ τι, όχι, άλλο. Πρακτικά, ένας τρόπος να το αποδείξεις δεν θα ήταν εγώ το είχα πει σε αυτό το μοντέλο, με RDD, Regression Discontinuity Design. Αν θεωρητικά υπήρχε αυτό, θα πρέπει να υπάρχει ένα discontinuity. Άρα, το να αποδείξω ότι δεν υπάρχει discontinuity, κάνεις.
Τι discontinuity θα πρέπει να υπάρχει? Θα πρέπει να δεις αν υπάρχει αυτό.
Χρονικά στα χρόνια, τις περιπτώσεις του καρκίνου στον πληθυσμό.
Δεν θα υπάρχει. Μπορεί να μην είναι discontinuity καταρχάς, αλλά υπάρχει ένας τρόπος να το κάνεις. Φαντάζομαι. Αν κάνεις αυτό που κάνουν για τους θανάτους από COVID, να το κάνεις για άλλους θανάτους.
Άρα αυτό που θα κάνεις εσύ
Είναι να βάλεις να δεις αν το COVID, ας πούμε, επειδή είναι, κοίταξε, το ideal, και αυτό να μην το έχουν κάνει και που να αποδείξω ότι δεν ισχύει, είναι να πάρεις αυτούς που έχουν κάνει COVID και να δεις πώς πάει ο καρκίνος αυτός.
Ναι.
Μερικοί έχουν τέτοια αρχεία και το κοιτάνε και τα δαμίζουν.
Εντάξει, το θέλει όμως
Τεράστιο.
πολύ συγκεκριμένα και με
Μεγάλα αρχεία. Να το κάνουν.
στην κυρία Τσπίγλου, ότι εγώ έχω τέλος του μήνα θα τη στείλω φυλακτικό κομμάτι όλη τη γράφη και μέχρι τέλος Μαΐου έχω σκοπό να πηγαίνει να στείλω το πρώτο draft ολοκληρωμένο. Δηλαδή, πάνω σε αυτά που έχω δουλέψει, τα οποία βγάζω, επειδή καταλαβαίνω ότι όσο αφήνω τον εαυτό μου να ψάχνει, χάνω. Οπότε λέω, αν δεν έχετε πει να σας στείλω τα συμπεράσματά μου. Προφανώς, αν θεωρείτε ότι θέλει κάπου που πες στο δουλειά μου, το λέτε, αλλά τουλάχιστον να έχουμε ένα κοινό έγγραφο, δεν είναι διορθώσεις. Δεν αρχίσει να μαζεύει έτσι, να αφήνω.
Σωστά.
Συμφωνείτε με αυτή η προσέγγιση?
Okay. So we talk what clusters are. Okay. As I was saying, in the public opinion polls, what do they use as clusters? The city squares, blocks. They go there, or buildings, and they take these as clusters. Now, we have three methods and combinations thereof. The simple random sampling, where each member of the population has the same probability to be selected. We have the stratified random sampling, where we divide the population and correspondingly the sample into the strata. And we can select from each stratum with simple random sampling or any other methods we want. And then we combine the results from each stratum into the overall sample, and we get the results. And we have the cluster sampling, where we have a sampling unit. Initially, we have the cluster. We select a sample of clusters. And then from the cluster, we take all the members, or we take a random sample of the members of the cluster, and then we combine the results in cluster level, and then if we did stratification in stratum level, and then in population level. In the study that I mentioned to you in the mobility, we use the university department as cluster. Okay, and we selected university departments, and then we did the analysis within the department, and then within the stratum, which was country and type of institution, etc., and then overall. Now, how does that affect the estimators? Well, first of all, you understand that the new estimators will come up with properties as the ones we mentioned in the previous chapter, so we can repeat all the tests the same way as we did them before, just taking into account the structure of the formulas here. The first observation is a simple random sample for the mean, which is the classical observation. What is the sample average, the sample variance? Simple things. In stratification, we have a different way of calculating the mean. We take the mean within stratum, and then we add them up, all the stratum means, weighted them by the weight of the stratum they belong in. Why is that important? And I can show to you how it works in practice. In essence, let me go directly here. I think it would be easier to do it like that. Let's say we had stratum here. And we have X here. Okay, and we had stratum 1. And I'm gonna make them extremely small here, don't think. 15 and stratum 2, 5. Okay, and let's see that these things were so these are random numbers from 5 to 10. Depending on which version of Excel you use, you have a different separator. Okay. And let's say that these are here are random numbers, but they are from 10 to 40. All right. So I have these numbers, okay? If I want to take the overall, the overall average, it comes out to be 1025, okay? This is my sample now. I did the average. If these things came of a population that for stratum 1 had 500 and stratum 2 had 2,000 members. This thing here is patently wrong because it treated them the same way when in fact it should do the following thing. So this thing should be multiplied by this over, I'm sorry, 2,500. My mistake, sorry. And the other thing should be multiplied by this. So the true mean was 16.96 and not 10.25. That's a correct estimate. Why? Because this estimate implicitly says that this average 7.2 corresponds to what is here, 15/20ths of the mean. Okay? And this thing corresponds to 5/20ths because it treats them all the same. But this stratum 1 is not 3/4 of the population, it's only 20% of the population. So it gave too much weight on these small numbers versus these bigger numbers. That was the 3-way. So the stratification method does exactly that. It is in the example that I said to you laughingly in the opinion poll, when we have, let's say we have 3 polls. 1, 2, 3, okay? And the people that voted for X were 100 here, 1,000 here, and 1,500 here, okay? And this was 200, this was 3,000, and this was 10,000, the sizes of the surveys. So in each survey, the part in question had 50%, 30%, and 15%, okay? I cannot take the average of this. It would be wrong, because they are on different number of people. What can I do? I can take this and say, all right, how many are these? They are 200, and let me add them up. So this first proportion that I see is this times 200 over 13,200. This is how they have, how much they have contributed to the answer. Now I will correct the others, don't get upset. The second group contributed 3,000. And the third group contributed 10,000. Okay, now if I sum them up, I'm done it right. It's 20% that they get. Okay? And it's only logical. It's close to 15%, but a little up more because the other two surveys. What is this number? It's a number that will happen if I took this thing and add it. Okay, the total number that said they voted for the party over the total number in the surveys. Okay, so it's the same way you calculate. If you see the numbers multiplication I did, you'll see that it simplifies and comes up to this. So this is the method, the stratification method, okay, that yields this variance. From that now, using the properties of the variance, we get this simple formula for the variance that works always. No matter how we did the stratification, how we selected to put the numbers in the strata, etc. Because, for instance, here I use NH saying that I have a different number of observations per stratum, okay? You might decide to have the same number of observations per stratum, as it happens in the Community Innovation Survey. The instruction from Eurostat is that you use 2,000 observations per country. So each country does its own study with 2,000 observations. And you have the same accuracy within its country, as we said in the beginning, right? The accuracy is a function of the sample size. But when you compare it, you have what? 27 times 254, you have 54,000 observations for the Community Innovation Survey, okay? And you combine it to get the European numbers using that NH, which is the stratum weight. Now, many times we use that proportional allocation of the stratum, of the data to the stratums, which has an impact on the way the variance is calculated. I have simplified the formula a little, and you see here the simplified version. The advantage of this has to do with the calculation of the sample size of the study in advance. Otherwise, it's the same calculation as this one, doesn't matter. Maybe it's easier to do, but we do everything in computer, so it doesn't matter. I'll show you what I mean about the sample size. And for proportions is the same idea, the simple estimates for proportions in simple random sampling, and the more complicated, but the same idea, weight times p, and here the weight multiplied by that, or here, if you think of the pH times 1 minus pH as s squared, then it's the same formula, right? It's WH times s squared over n, the variance of the estimator. I could have here a third choice, which would have been the cluster sampling, but I didn't do it because it's much more complicated formulas and will make our life more difficult. And also I want to point out that we have a third estimator, which I didn't touch upon, since we need to leave some time, which is the ratio estimators. It's a quite more complicated process because when you have ratios, you have numerator and denominator as a random variable. So all these simple calculations don't work out, and you have to have much more complicated variance estimation procedures and estimator calculation procedure as well. It's just that it's not the most common estimator. Usually in all the studies we do, we have proportions and means that we compare. Ratios would be if we had some sort of what would be a ratio? For instance, number of students per teacher at the school. Okay, that's a ratio estimator because the number of students is a random variable, the number of professors is a random variable. When you divide it to random variables, you get that ratio, which is complicated. Or certain indices that we use for evaluation programs may come as ratio estimates. Okay, and that would be useful there. So how do we calculate the sample size? Well, the sample size is calculated. I give you the formulas directly. I didn't want to show you how to do the math. Doesn't matter. But it's all of this in the simple random sample is based on knowing something, which is the variance of the population. Okay? Since we hardly ever know the variance of the population, what we usually do in these cases, either we look back at other studies that are of a similar manner, and we borrow the variance estimate from them, or we conduct a pilot study. In other words, we'll say, well, we want to do a European study, all right? It will definitely need 5,000 people or entities that we want to sample, and we're not going to do a study on 200 and 300. So I can feel safe to select 500 to 1,000 observations, estimate the variance, go back to a sample size calculation, and then the observations I use as a pilot, I keep them. I don't throw them away. So if I do the calculation and it says I need 3,000 observations, I have 1,000 from the pilot, I get 2,000 more. Okay. I just have to be careful in these cases to exclude this 1,000 from the population. So when I go and get a sample of the 2,000, I don't get somebody from the pilot again and look stupid in their eyes when they receive the mail with a questionnaire again. All right? Not to mention they might answer it again, and then I have the same observation twice in my sample, and that creates some bias issue. That's for the S-square that I need for the fixed variance of the estimate, and also for the fixed accuracy, the maximum estimate on error, in other words. And I need an estimate of the mean if I try to get the coefficient variation. To be honest with you, in my view, I would prefer to use samples that are based on a fixed maximum error. Why people want to work with the coefficient of variation is completely beyond my understanding. But they do it. It's very common. There are all theories about it. I don't know why. Even in the book that I teach sampling theory from, it has a chapter that says that the coefficient variation of an estimate should be roughly 0.05. Why? I don't know how they got it from. But anyway, let me just stick something up here like that too. I don't know why. Got it. Okay, now, when I have stratified sampling, things are a little bit more complicated. Because in the stratified sampling, as you can see, I need estimates for the strata. Okay? I need estimates for the strata. And so, hold on a second, but I haven't done something. SRS, systematic proportion, STRS. Oops. You know something? I have destroyed my. You see, I have done something. The cut and paste method has some problems, which is, and I'll fix it here because We'll have some difficulty if we don't do it here. Okay. In place of this, I need this. Okay, here I need to fix these things. Now, what happens in the case of the stratified sampling, we need to get the variance within the strata, because that creates the thing, and so we have that problem. That we need to have a pilot study as well. Okay. Okay. Now, what happens is the following. These formulas are directly derived from the estimation process. Just let me make a point about the proportions. The proportions have a property. The variance we use, which is 1 minus p, is a concave function that has a maximum at p equals 0.5. Because it's p times 1 minus p, it's p minus p squared. The derivative is 1 minus 2p, and solves for 0 at p equals 1/2. That means that whenever I want to estimate a proportion and get a minimum variance, for instance, to get the best result, I'll go for the worst scenario, which is the biggest value of the variance, which is 0.5. And then I'll get the biggest possible sample. And if the proportion is lower, I'll have better accuracy. So I have spent some more money in selecting more people, but I've gained in accuracy. That's true for the variance, specific variance. It's true for the specific maximum estimation error. It's not true for the coefficient of variation. The coefficient of variations has a, how can I put it? A peculiarity, which is for small values of the percentage, the coefficient of variation takes big values. And for big values of the percentage, it gets small values. So we cannot work with the trick of 1/2, because 1/2 just is the midpoint of the coefficient of variation we could get. It's not the maximum. And there's no maximum because the maximum tends to infinity as the p tends to 0. So we're not going to do that. For that case, we'll need to do a pilot study, but the others we don't need a pilot study. For the error now, I have it written like that, but what I should have, which ends up being the same, it's this calculation here, where for p's I use the 0.5. So if I use a 0.5 here, then that becomes 0.25, goes out, and the sum becomes 1, so I end up with the same formula. I assume, in other words, that the value is 0.5 in every stratum, okay? Even if it's not. In this way, I get the maximum sample. So this way, I can design the studies, which is something that we might need to do, okay?